So in this video, I want to talk about inverse functions, specifically prefacing the more stuff we're going to do with inverse functions and calculus later on. I just kind of want to revisit what an inverse function is to begin with. So the whole purpose of this video is to gain a better understanding of just inverse functions in general prior to dealing more with calculus. For example, I want to start off with talking about the definition of an inverse function. So an inverse function, I'll write it as f with a -1 and essentially the exponent. It's not really an exponent, but f with a little -1 of x is going to be called the inverse of f of x if two things happen. Number one, if I take the original function f of x and I plug it in, if I compose it into its inverse function, I should be able to get just plain old x, nothing but x back out when I finish simplifying it. Additionally, the other thing that's required to happen is that if I take the original function f of x and I plug the inverse function f inverse of x into it, I should also get x. As in, no matter which order I do things in, I should get the same answer out. And it's always just going to be plain old simple x. And the reason this is because what the inverse function is essentially designed to do is if the original function takes x and turns it into a y, so if my original function f takes x's and turns it into y's, what should happen is my inverse function should take those y values and return the original x values. It should take those y values and turn them back into x's. So whatever the function f does, f inverse undoes. And so the question kind of leads us to here is, well, how do I know when a function can be inverted? When can I find the inverse of a function? And so I'll talk about that for a second. So f of x has a unique inverse, as in can be inverted, specifically in one instance, and it has to do with being 1-to-1. And you've guaranteed heard that word before, 1-to-1. Um, but you may not know exactly quite what it means. And what it means is that 1x goes to 1y. So 1x goes to 1y. That means that every x has a single y as its counterpart, and vice versa. One y value goes to one x. It's both directions. So that's essentially the thing is you're not going to have any x values that repeat, and you're not going to have any y values that repeat. The common thing that we look for in a graph, remember, if it's a function, we look for the vertical line test. For a 1-to-1 function, we also check the horizontal line test in addition to the vertical line test. And so all that's designed to do is, again, if the horizontal line touches it in exactly one place, it still is a 1-to-1 function. And so let me kind of just go from here and talk about geometrically. What am I looking for? Well, let's start off with this function right here. This is a exponential function that I just graphed. And what I want you to notice about this function is it's nice and kind of pretty, in that it has a nice sloping curve all the way up. And it is a function because at every x value, there's only one place where it would touch the graph as a y value. Okay, and so notice I'm trying to draw these vertical lines in here where you see how each x only goes to one y. Now, in order for this to be a 1-to-1 function, the same thing sort of has to happen with the y's, is that every y value should only be able to touch the curve in one place. That's one x value. So it has to pass the horizontal line test too. So once I check both of these things, if I want to find the inverse of this graphed function, what I need to do is I need to take the coordinates, and I'll start off with an easy one. Let's start off with 0, 1, which is right there. And all I'm going to do is I'm going to switch the x and y coordinates. So it was at 0, 1. Now I'm going to put it at 1, 0. So I'm going to have a point right there. Let me add in a few more points just to get the idea of what's going on. So the next point I'm going to use will be this point right here, which is 1, 2. And if I switch the x and the y's, that puts me at 2, 1. So that's its corresponding inverted point. Let's do another one. We'll do 2, 4. And that point will be all the way over here right on the edge of my graph at 4, 2. And we'll do one more. We'll do this one back here at -1, comma 0.5. And what I'll do, again, switch x's and y's. So it'll be 0.5, comma -1. So my graph should look a little something like this. Now, you may be looking at this and thinking, hey, this looks like it's got a nice little bit of symmetry since all we're doing is switching the x's and the y's. And you're exactly right in that perspective. If you think back to geometry, this is actually a transformation. This is actually a reflection. And I can draw my line of symmetry right here. Okay, so there's my line of symmetry. And again, like I said, this is a reflection. It's actually a reflection over a pretty interesting line. It's a reflection over the line y equals x, because all I did was I switched the x's and the y's. Now, it's all fine and dandy to talk about the definition of a one-to-one function and an inverse function and all of this other stuff, and to look at it graphically. It's another completely thing to think about doing it algebraically. So let me start off with an algebraic function. Let's go with y equals, we'll do 3x minus 1 over x plus 3. So we'll talk about that function. Now, that is that is a function. It's a rational function, and I want to show you how to take this nice, pretty rational function, which I could have also written as f of x equals 3x minus 1 over x plus 3. I can take this function and I can invert it. I can turn it into its inverse, where essentially it undoes what this function does. And probably the most important thing to do first is to do kind of what I was doing graphically, which is I need to switch the x and y variables. Okay? So that means every time I have an x, I'm going to turn it into a y, and every time I have a y, I'm going to turn it into an x. Well, if x equals 3y minus 1 over y plus 3. Now, my goal now is to solve for y. I want to isolate that y variable. So what I'm going to do first is multiply both sides by y plus 3. All right, so here I go, y plus 3 and y plus 3. There we go. That should eliminate this denominator. And on the right-hand side, we'll be left with 3y minus 1. And on the left-hand side, we'll have x times y plus 3. So we'll need to distribute this x. So x times y makes xy plus 3 times x, which makes 3x. And like I said, we're solving for y, so I want to try to get all my y's on the same side. I'll move everything over here to the left side, so I'll subtract 3y from both sides. All right, and that'll give me xy minus 3y plus 3x equals -1. And I want to get all the y's by themselves, so I'll move that 3x over. Okay. And so I'll have xy minus 3y equals, that's a -1 minus 3x. You could write it in the other order and do -3x minus 1. That would still be correct. And the last thing I want to do here before I get the y completely by itself is I'm going to factor out that y. Notice it's a common factor here. Okay. So I'm going to factor out the y. And if I take away a y from xy, I'm going to be left with just x. If I take away a y from a minus 3y, I'm going to be left with a minus 3 equals -1 minus 3x. And now I'm going to just divide everything by that x minus 3. And that gives me y by itself. So we'll have y equals -1 minus 3x over x minus 3. And that is going to be my inverse function. So I'll write that over here. F inverse of x is equal to -1 minus 3x over x minus 3. All right, so notice again, we talked about the definition of an inverse function, that we should be able to get x out if we plug it into the original function, if our operation is composition. We talked about what one-to-one was and how we would look at it on a graph. Remember, again, it has to pass the horizontal line test. We talked about inverses and their original functions are a reflection over the line y equals x. And we talked about how to find an inverse function algebraically. Hopefully this helps you guys prepare for our next part where we talk more about using inverse functions